Hello and welcome to this video on how to do sample size planning for latent class analysis. My name is Geiser. I'm an instructor with QuantFish. One question that I often get is, how large does my sample size have to be for a latent class analysis? And that question is really difficult to answer because it depends on so many factors, such as the number and quality of indicators that you have of your latent classes, the number of classes that you want to extract, whether your indicators are binary or ordinal with more than two response categories, and other factors as well. So then how can we determine the appropriate sample size for a given latent class analysis? The best way to do this is to simulate a specific model for different sample sizes to find out whether that model works well in terms of different criteria at those different sample sizes. And in that way you can determine the minimum sample size at which your model performs well in terms of, for example, parameter estimates, standard errors, fit statistics, and other parameters. So let's get started and let's take a look at how a simulation study can be done for sample size planning in latent class analysis using the Mplus software. The Mplus software makes it really easy for you to run latent class models, but also to simulate latent class models so that you can determine the appropriate sample size. The same principle can be applied also to other models such as confirmatory factor analysis and structural equation modeling, for which sample size planning can also be done via simulation, and I have other videos on this channel in which I show that. So here, first of all, I have an Mplus output file for a latent class analysis of actual data. And so that is one way in which you can start or set up your simulation by using a previous run of a model for a given sample that you already have, and then use those parameter estimates of that run as simulation parameters. So meaning those would be best guesses, so to say, realistic estimates from a real data application that could be the basis for your simulation. Of course, that only works if you already have data. If not, you would have to specify the parameter estimates by hand, and I'll show that later as well, how that can be done. So in this scenario here, I already have an analysis of real data, and one question could be, would this also work for a smaller sample size? So in this case, as we will see, I had a latent class analysis estimated for 861 cases, and so maybe I want to do a follow-up study, or I want to do a study in a new population or different population, and I want to know, could I do this with fewer cases? For example, could I do this with just 500 cases? And so then I can simulate this model using the parameter estimates from this run for 861 actual cases as population parameters. That way I can ensure that my population values are realistic because they were obtained from real data. And so, as I will now show you, Mplus makes it really easy for you to save parameter estimates from an actual data application to use in a simulation study. And there are actually two ways to do this, as we will see. So here you can see this is the syntax or input file for a 3-class latent class analysis model. I'm analyzing 5 binary items here. So x1 through x5 are the items that are used as latent class indicators. They are dichotomous and they are therefore listed here under categorical. Mplus will automatically determine that there are only 2 response categories. I'm extracting a latent class variable with 3 latent classes here in this case. And you can see I have a specific subcommand in the output command that says sValues. The sValues command allows you to save the model statement for this 3-class latent class analysis with the estimated parameters as starting values. And then you can copy and paste that from the output into a simulation input file, and you can simulate your model. That's one way that makes it really easy for you to specify population parameters in a simulation input file in Mplus, and that can be done not just for latent class analysis but also for other models such as confirmatory factor analysis or structural equation modeling. A second way to do this in Mplus is to save the estimates to an external file. So with the save data command, the estimates from that model will be saved to an external file that here I named est.dat, and then they will be in a specific order that Mplus recognizes when it runs the simulation later, and so it'll then pick up the parameter estimates from that file and use them as population parameters for the simulation. So that's also very convenient. That way you don't even have to do copy and paste from the output, because Mplus will then just simply read those estimates from your saved file. Now this analysis here is based on 861 cases. We can take a look at the model real quick. It fit the data reasonably well. And when we go to the plot option, we can take a look at the conditional response probabilities, so we get a sense for what those looked like. So I'm going to plot the conditional response probabilities for the 5 items across the 3 classes. You can see there was one class, the green one here, class 3, with low response probabilities on all items. The blue class had high probabilities for items 2 and 3, and class 1 had high probabilities for items 1, 4, and 5. So the classes were clearly distinct. There were clear qualitative differences also between the classes. And so this might be a prototypical kind of model where we have one class that's all low, and then 2 classes that are high on specific items and then low on other types of items. So this model I'm going to simulate now, and so I want to find out whether this model would also work okay for a smaller sample of, let's say, 500 cases. So I'm now going to show you the Mplus simulation input and output file for a simulation of 500 cases. And so here you can see the input instructions or syntax. This is a Monte Carlo simulation of the 3-class latent class model for a sample size of 500. And we have the Monte Carlo command here. The Monte Carlo command is used when you run a simulation study in Mplus. And we also have to use the names subcommand here to define the variable names. So I named them the same way as they were named in the actual application, x1 through x5. I defined them again as categorical, and I used the generate command to tell Mplus that those are supposed to be dichotomous variables with only one threshold. And then also I told Mplus that 3 classes should be generated in the population model with a gen classes command. I selected 500 as the number of observations for each replication of that simulation. I selected 1000 replications, so Mplus will draw 1000 samples of size 500 from our population 3-class model and estimate the model in each of those 1000 replications or samples, and then it'll give us a summary of the parameter estimates, standard errors, and other things across those 1000 replications, so we can see whether the model worked well with a sample size of 500. The seed value gives a starting number so that Mplus knows, so say, where to start. It's a random number, and it doesn't really matter which number you choose, but it's maybe a good idea to vary that number to see if it matters for the results or if the results are dependent on the seed value. Furthermore, you can see that we're now referring to this data file that contains the estimates from the actual data run here. And so we're referring to this data set in 3 different subcommands: in the population subcommand, the coverage subcommand, and the starting subcommand, so that Mplus knows that it should draw the estimates from this file. So we're not going to specify a model here at all, but rather we're telling Mplus, go find those parameter estimates for the population model and for calculating coverage and for use as starting values in each replication from that file that is named est.dat. And that works really well. So Mplus will find that file, it'll just take those estimates, it'll know in which order they are for a latent class analysis, and then It'll just use them for your latent class model. Now, what is really important is that when you do it like that you do include the starting value command, because you want to make sure that Mplus also uses those parameter estimates from that file as starting values in each replication when Mplus fits the model to those Monte Carlo replications or samples. And that is important because otherwise you might run into a label switching issue, which means the order of the classes is arbitrary. It doesn't matter which class is class 1, class 2, class 3 in principle. It's interchangeable. And so it might happen if you don't have proper starting values that Mplus mixes up the classes. So sometimes class 1 is then class 2 in another replication and so on. And then you get a lot of problems when the results are being summarized or averaged across those 1000 replications, because then the average may not make sense if class 1 is not always class 1. And so using the starting values ensures, or at least makes it very likely, that the classes are always in the same order for each replication, so that when the results are then summarized, that summary actually does make sense. So that's a very, very important subcommand here when you use this external file system. Furthermore, we run a 3-class model. So we run a correctly specified model in each of the replications, and we just want to see, does this model work okay for a reduced sample size of 500 observations. Furthermore, we specify type equals mixture as we would in a real application, and we ask for tech9 output, which gives us error messages, warning messages, if any. So for example, if there was an estimation problem or convergence problem in one of the replications, then Mplus would give us the replication number as well as the type of warning message in the tech9 output. So let's go take a look at what this output here looks like. You can see input reading terminated normally, so that's a good sign. And then we have 500 observations that are being simulated. We requested 1000 replications, and 1000 were also completed. That's important to check, because if you have convergence issues and not all of your replications converge, then that might indicate a problem with the sample size. So let's say if you have only 300 completed replications out of 1000, that's not a good sign. This would indicate that this model does not work well for a sample size of 500. When we scroll down further, we can see that we get a summary of model fit information, and here specifically what is of interest is the chi-square distribution approximation. One chi-square statistic that we often use for model fit evaluation in latent class analysis is the Pearson chi-square statistic that you can see here. And so we want to make sure that the chi-square distribution is well approximated by the Pearson chi-square test statistic with a sample size of 500, because remember, a chi-square test relies on asymptotic theory, so on large sample theory, and this may not be large enough. When you have a latent class analysis and 500 cases, perhaps that's not enough for a reasonable chi-square distribution approximation. And so we can check that by looking at those statistics here. And so you can see the mean Pearson chi-square computed across the 1000 replications was 14. The degrees of freedom of our 3-class model with 5 indicators is also 14. And so you can see that the mean of the Pearson chi-square was very close to the degrees of freedom, as it should be for a correctly specified model. And so that's a good sign that we are close to the 14 degrees of freedom with our test statistic on average. Furthermore, we can look at the expected versus observed proportions of the chi-square distribution, and we can see that here when we look at the expected distribution, that would be the theoretical proportions from a chi-square distribution, and we can see here that the 0.05 level that we typically use for model testing was well approximated. So you can see that the empirical value across the 1000 replications, or the empirical proportion, was 0.052, which is very close to 0.05. And you can see that overall there's close correspondence here for the observed and expected proportions, which means that the chi-square distribution was well approximated for this model for a sample size of 500 using the Pearson statistic. So that's a good thing, which means we could trust that statistic when we do tests of model fit, when we test the hypothesis that the latent class model fits exactly in the population. We also get the same output for the likelihood ratio chi-square statistic, which is an alternative statistic for model fit testing that is often used also for nested model testing. And so here you can see that the approximation is less good. The average likelihood ratio chi-square was 15 with 14 degrees of freedom, so it was a bit large. And you can see too that we have not as good of a chi-square approximation here. For example, for a 0.05 level, we have 0.083. That's a bit high. Also for 0.10, we have 0.15 almost. So that's not super good. And that's typical. That's a typical result for the likelihood ratio statistic. The likelihood ratio statistic works less well in smaller samples. The Pearson statistic is more robust to smaller sample sizes, or tends to be more robust to smaller sample sizes with latent class analysis model fit testing. Overall though, those results are good because they show us that the Pearson statistic could be trusted for the sample size, so that's good. And then next, we're going to go down to our parameter estimates under model results. And so here we find the average estimates across the 1000 replications, and we can compare those to the corresponding population parameters. Notice that Mplus gives the results in logistic regression or logistic threshold metrics. So those are threshold parameters in a logit metric that can be converted to probabilities. And so what we can do is we can compare the average estimates to the corresponding population value. For example, the threshold for item 1, x1 here, which would correspond to the conditional response probabilities of that item, we can see that the population threshold was negative 0.942 and the average estimated threshold was negative 0.9994, which is reasonably close. So for that threshold, there wasn't a lot of parameter bias, which is also good because it shows that with the sample size, we wouldn't have any bias for that item. It looks less good for other parameters. For class 1, those all look pretty good. For class 2, you can see that there are at least a few that are not so great. In particular, for item 3, you can see that the population value was negative 1.249 and the estimated average value was negative 2.949. This is a lot different. So there's some bias here, and that's potentially not a good sign. So we'll see later why that happened, but for now, notice that that's not great because that indicates parameter estimate bias. Also, we can do the same thing for standard errors. So we can look at the standard error average, or the average estimated standard error across the 1000 replications, and compare that to the Monte Carlo standard deviation of the parameter across the 1000 replications. And so here we can see that for some parameters, it's very close. For example, for item 2 in class 1, there's hardly any difference, there's hardly any bias. For others, it doesn't look as good. For example, item 3 in class 2, there's quite a bit of standard error bias. Also, the standard errors seem high for that item, so that's not great potentially. But again, we'll see later why that happened and what this potentially means. But so in this, what I want to show here basically is that you can use this output to assess parameter estimate bias and standard error bias by comparing those two columns and then also comparing those two columns with one another respectively. Now let's talk about why do we find some parameter bias here and some standard error bias. A sample size of 500 seems pretty reasonable for 5 items in LCA. So when I first saw these results myself, I was pretty surprised and I thought, oh, this is weird. And so then I figured out the reason why this happened here. And so you can figure this out, or I figured it out by looking at the Tech 9 output at the very end, the Tech9 output gives us error messages for each replication if there were any. And so it's very important when you do a simulation like that, that you do check Tech9 output, because otherwise you may not understand what's going on. The Tech9 output tells you in each replication, was there something that didn't go well? And so here you can see we get a lot of error messages or warning messages. It starts with replication number 3, so the first 2 were fine, and then 3 wasn't. There was something 4, there was something 5, there was something 7, 8, so lots and lots and lots and lots of these messages. And they are pretty much all the same as far as I saw. They all indicate that there were boundary parameter estimates, meaning there were threshold parameters that were set to extreme values in the estimation. Those are values that correspond to probabilities of 0 and 1. Which are boundary parameter estimates in latent class analysis. The problem when boundary parameter estimates are encountered during estimation is that you have a parameter estimate that is potentially wrong, and you also don't get a standard error. And so therefore then it messes up your entire calculation of the average parameters and also of the average standard errors across replications. And so this explains why we get this bias here for some parameter estimates in our parameter estimates table, because there were boundary parameter estimates for some of those, in particular here for X3. So those were items that had very high or very low probabilities in the population model. And so then this shows us that with a sample size of 500, a lot of these will end up being boundary parameter values, which may not be ideal. So this may be a reason to reject that idea of using a sample size of 500 for this model and rather using a larger sample. Or not, it depends. So if you feel like boundary estimates don't really bother you so much, then you might be okay with that potentially, but in other cases we may not want that. And I have a separate video where I discuss boundary parameter estimates in LCA in more detail, what they mean and why they can be potentially problematic. So now in this case I would say let's move on and let's see what happens with a larger sample, because these are clearly sample size dependent. And so to show that, I also simulated the same model for a sample size of 2000. And so when we go take a look at the same simulation of the same model, but for a larger sample size of 2000 cases, and we go back to our Tech9 output file, or output portion here, then we can see there were only 6 such messages for a sample size of 2000. So 6 out of 1000 replications. That's not bad. So I would say that is reasonable. And then when we go to our parameter results table, we see that with 2000 there was no problem. Even for the item number 3 in class 2, there was hardly any parameter bias, hardly any standard error bias for any of those items here. All those estimates were very close. So 2000 would definitely be an okay sample size for this model here. Now, the last thing that I want to show you is that you can also set up a simulation of a latent class analysis model manually. So let's say you do not have model estimated already, you haven't collected data at all, so you don't have a template model that you can base the parameter estimates off of for your population model in the simulation, and you have to come up with parameter estimates manually. So then what you can do is you can take the estimates from if you have a model, you can take the estimates from the S values output here. So the model command with final estimates used as starting values that I got with the S values command. And then you can copy and paste that into a syntax for a simulation. And then you have all the relevant commands already that you can use to set up the population parameters manually. So what that looks like then in a simulation is shown here. So let's go take a look at that input file. So you can see that for a manual Monte Carlo simulation of a latent class analysis model, we have to again use the Monte Carlo command with the names categorical, generate, gen classes, n observations, n reps, and seed subcommands, as well as the classes command. And then now we're specifying our model manually using the model population command rather than using the option where we draw on estimates that are in a given file. And so that way you can write whatever you want. So you can set up the threshold parameters for the class sizes under overall, and you can also set up the threshold parameters that correspond to conditional response probabilities within each class by using class specific subcommands here. And so in this case I copied and pasted the parameter estimates from the S values output from the actual data run. But if you don't have an actual model, then at least this gives you a template for how to set this up. You need an overall command for the class size parameters, and you need class specific statements for the conditional response probabilities within each class that are specified in this way. And after the model population statement, you also include a model statement so that this model is estimated within each class, and you provide those parameter estimates as starting values like we did earlier using the starting subcommand. I hope you found this video useful to learn about how to simulate a latent class analysis model for sample size planning. If you did, then please subscribe to this channel. Check out the description for additional resources, including courses that QuantFish offers on latent class and other mixture models, and I'll see you next time.